Hey.
What's up?
Oh, worn out,
Yeah, I hear that.
wiped,
Quite.
totally wiped today.
Do you want to talk about it afterwards?
Uh,
I was wondering if there was big news, really. I'm just being selfish.
no, just I'm still negotiating and it's so stressful. It's so incredibly stressful and keeping me up at night. And then I got this crap and sorry, I hope edit that out.
Yeah, right. We're recording, man. Some
No,
days,
it's
some
not
days work
as,
feels hard.
oh yeah, sorry. That was the sleep deprivation talking there.
That's all right.
All right.
You
On a
ready to turn it
positive
on?
note, huh?
Yeah, on a positive note.
On a positive note, the quiz going into today, I just looked at them all. They generally got the logic right. It was good. And I did vignette, got through vignettes too, and not bad, you
All
know.
right. Good.
Not bad.
Progress.
Mostly B's and low A's. So I was going to address that at the beginning, and then we can dive right in.
Awesome. That
Cool.
is progress, and
Yeah,
progress will
yeah, it's
grow.
material progress.
Sweet. All right. We'll admit everybody and then we'll
All
get going.
right.
Admit, where do we get to admit all? It's probably at the top. Admit all.
Hello, hello. Hey, team.
What's up, crew?
Hey,
Evening
everybody.
or good night.
Good
Late for you.
evening. Good night.
Ben and I have to stay awake at least 2 more hours. So no good night yet.
Yeah. Whew. I ain't gonna lie. I'm wiped. So,
We're
you know,
gonna keep the
I
energy
do
up. We gotta help
I do
Dr.
my
Meng.
best. I
Yeah.
do my best today.
Yeah.
Oh, all right. Let's just check a couple things. So, we got a lot to go through today. So I wish, Stuart, but we got so much to cover. So we're gonna dive right in. Um, So let's see. First things first, the feedback from yesterday is, hey, we need to get on our stuff on the vignettes. So what you will notice is I was able to get in and get the second vignette exercise completely graded. Um, and I'll share a couple of things on that. One is overall, I thought you all did decent job. Like, not bad, really not bad. Taking it from the logical arguments and I would say kind of looking back at those, that appears to be where you all struggled the most is breaking down the premises and the conclusions. But overall, I thought you all did a very nice job of transitioning from the logical arguments to the testable statements. And what you're going to see, I tried to record a quick audio feedback for each of you and provide a little bit of text feedback to give you some examples. So I hope that that's helpful for you. And the biggest piece of feedback overall on those statements, those testable statements, which is also going to be true of vignette number 3, which I'll talk about in a second, is getting it down to the operational definition. Is it specific enough? Is that statement specific enough to know what you're measuring and how you're measuring it? And so a lot of the feedback you got from me, and mostly where the points were deducted, were in statements that were made where it was too ambiguous. It didn't have enough specificity. But again, overall, I was very pleased with the progression you all made on that. Um, yeah, Becca, that's a good example. So there were some cases, maybe I'll use a generic example. There was one in particular, I think some folks struggled on where there were a number of examples of how employee performance was projected to be better in a hybrid versus a in-office environment, or an in-office versus virtual environment. And some people would say things like the performance is better, or performance is better in office than in virtual. A better answer, that some of you were able to drill down into, is defining what performance is, going back to the case and talking about people who work in office collaborate more, work faster, and make better decisions. That's a little bit more specific. So it's not a huge difference, but you can see in that case, in the second example, where you're defining organizational performance, you're getting closer to the operational definition, which is really critical when you go into the hypothesis formulation. So that would be an example of that. And I think with every single person, I took at least one example, in most cases, more than one example, and demonstrated, here's what you did, here's how I would tweak it. And you either hear that through audio or via text or both.
Who
Um,
from the video that you guys were supposed to watch, did anybody call out the place where not having an operational definition created some squishiness in who was right?
That was the definition of turnover, right?
Ding ding, right?
Bingo.
So we'll talk about that later tonight, but that was a place where, to Dr. Ben's point, how you define turnover really determined who was right about their insight, didn't it?
Yep. That's a great point, Chris. That's a good example. And what I'll also share is that as we move on, because Chris and I we didn't do a very good job of grading those vignettes in sequence. And that's a good lesson learned for us, because I think moving forward in the course in the future, it makes a lot of sense, the feedback you all gave us, that before you move on to the next step, you need feedback on the prior. And so the commitment we made, and I tried to make in the grading of this, is not to, I didn't want to ding you on points for, well, as we move into grading vignette 3, if you struggled on vignette 2 and that led you to struggle on vignette 3, we're not going to deduct double points. Like we're not going to double penalize you for that. We're going to reflect the fact that you didn't get that real-time feedback, and we're going to take that into account and be a lot more lenient in the grading of vignette 3, so that you don't like get double or triple penalized for it. So we're going to try to really focus on, and that's true for the new vignettes, for example. So we're going to be um, um, try to be mindful of that with the grades. And so just wanted to make sure that you're aware of that. Like we're not gonna ding you because we didn't give you proper feedback at the right time. That's on us, not on you. Um, the other thing I wanted to address too, I was looking at I did go through the grading for the quiz coming into today. I was very pleased with what I saw. I think with the distribution question, you all nailed it. The definition of the different distributions, the normal, the negative, the positive. The logic I saw in everybody's for the second scenario, which was essentially that training department where you're giving a really difficult pre-assessment. Every single person got the logic correct, that you're going to see more scores end up on the low end of the distribution, which is exactly right. The only minor thing I noticed was that there was a little bit confusion as to what kind of skew that's called. So I'll pose it to the group. If you have a distribution of pre-training assessment scores where people are not going to perform well, and you have that distribution and most of the scores are bunching up on the low end of the distribution with the tail pointing to the right, what kind of distribution is that called? Positive skew. Yeah, positive skew. So I think a lot of, and this is normal, by the way, the first time you see the skew, it's tempting to think, oh, the scores are on the negative side, so it's negative skew. It's the opposite. The name of the name of the skew is the direction that the tail goes. Didn't ding anybody on the points because your logic was correct. Like you understood the concept. So no points taken off for that. But I was really pleased that you all clearly understood the principle. And then the second part that I'll pose to the group was if you if you have that positive skew distribution and somebody said, what's the general central tendency? There was a variety of different answers here. What do y'all think? Would it be the mean? Would it be the median? Would it be the mode? Some of you had trouble with it and you called it out, which was cool. Median.
Median.
I tend to agree. I tend to agree. I think generally speaking with that kind of data, the median would probably be the way to go. But there's no guarantee that that's true. So again, I didn't ding you if you got that wrong. I just put a note in there. But most of you got the logic and the logic around it right. So I was very pleased with what I saw in the quiz. So anyway, this is a little bit of live feedback on those two assignments. I was very pleased with it on my side. So I guess any thoughts, any questions from the group before we dive in? You got it. You got it. And thank you for the feedback. We try to take the feedback and act on it. Okay, so we got a lot to cover. Let's dive right in. We're going to finish our lecture and then we're going to dive into some actual exercises with the final project data. So I know we want to use as much time for that as possible. Okay, so we're going to start out by let's see. We kind of already talked about this. We're not going to jump into groups. But let's do it as a big group really quickly, just to kind of test our knowledge on the measures of central tendency. So let's say, for example, and feel free to jump in the chat or just jump in verbally. All right, you're calculating the typical, and I use that word intentionally, typical annual compensation for the population of employees across all departments, all levels, entry level to C-suite. Okay, I like where your finger's going, Tyler. What measure what shape would that distribution look like? Most likely. Anyone? Positive skew, right? So you're going to get a lot of lower compensated folks bunched up at the bottom of the distribution. It might be slightly bimodal depending on the populations. And you can see that long tail out to the right. And so in that case, what would probably be the best measure of the typical compensation? We did a little bit. The median, right. The median, maybe the mode. Right. Exactly. Why not the mean though? What's wrong with the mean?
It's affected by extreme values.
Right. That mean is going to drastically, exactly. It's going to drastically overestimate the center of the distribution if you were to add all the executive compensation in that data. It's spot on. Exactly, Stuart. Yep. Okay. You're calculating the most common reasons for leaving collected from exit survey data over the last year. That's a tough one, but any guesses? The rationale is the most important. Bimodal. Could be bimodal, could be multimodal. Hard to say, but I agree with you, Tyler. I think it's probably going to be like a bimodal or multimodal because these are categorical, right? It's not numerical. What would be the best measure of central tendency here? Mode, exactly, Stuart. Exactly, because we have categorical data. Excellent. Okay, so the last one, we'll just skip that. I think we all get the point. Very, very good. I think you all really understand this. That's great. So now we're going to build on that, and we're going to jump into the second category of measures of descriptive statistics, which are the measures of dispersion. And if you recall from last night, there's basically three measures we're going to talk about. There's the range, there's the variance, and there's the standard deviation. So let's start with the range. The range is the easiest, probably the easiest by far. It's kind of like the mode of central tendency, is the most straightforward and easy to calculate, because really all we're doing is we're looking at literally the full range of the distribution. We take the lowest score, the lowest value in the distribution, way on that left tail, whatever that value is, and then we find the highest value in the distribution, way on the right tail, and then you just subtract the two. And what's that? So we use that example, that little data set. We're going to come back to that today and use that again, that little simple data set. Just like we do when we calculate the median, I just rank ordered the values from lowest to highest, take the highest value, subtract the lowest value. The range of this distribution is 7. Very, very simple, very straightforward. Now, the range isn't super, there are some uses for it. There are some cases where it might be really useful, but it's not particularly used often in inferential statistics. But the variance and the standard deviation are, and they are also significantly more complex to understand. So we're going to spend a lot more time on the variance and also the standard deviation. These measures, oh, go ahead.
One place you do see range, and to Ben's point, it's not used for very advanced math, but compensation ranges are a big thing. So how much overlap you have between bands or between job codes, that's one place where you're going to see range applied a lot. But to Ben's point, it's not really used in statistics. It's typically just used for standard reporting and basic arithmetic.
Yeah, good point. And Stuart brought up a good question. I think I saw the recording when we started. Is that? Yeah. I can't see it on mine. Yeah, it is. It is. Yeah. Thanks for checking those, Stuart. And thank you, Tyler, for checking on that. Okay, so let's get to the slightly more complex measures, but also more important. We're going to start with the variance, because while the standard deviation you're going to find is more probably intuitive to understand, to get to the standard deviation, we have to start with getting to the variance. And so the variance takes a couple of steps to get to. There's this nice fancy little calculation. We're going to break this down to kind of demystify it. It looks very complicated. It's actually remarkably simple when we break it down. But basically, to do that, before we get to that calculation, the way I like to think about calculating the variance is just a very simple step-by-step process. And I like to start with the most simple, basic things first. First thing, what's the sample size? Or if you're doing calculating the variance for a population, what's the population size? What's your N, in other words? The second step is now you have to go calculate the mean. So you probably remember yesterday when we were talking about the measures of central tendency, and we talked about the mean being really important for actually understanding this. We're going to use it a lot in inferential statistics, and we're also going to use it in calculating the variance. And we're going to explain this in some visualizations with the distribution in a bit. But basically, that's the second part. What is the average or the mean of the distribution? And then what we do, and this is where this little, if you remember sigma, anybody remember what the sigma stands for in the calculation? The sum. I saw Becca's mouth. Yep, the sum. So the sigma here just means we're summing some values. So what we're basically doing is we're taking each individual value of the distribution and we're subtracting it from, or subtracting the mean from the value. And so that's what you see here. This X represents each individual value in the distribution minus the mean. And then what we're doing, so we're taking all those differences and then we're squaring them. We sum those squares up. And then we divide by n minus 1. So the sample size minus 1. We'll talk about why that's the case later. But for now, The
Excuse me for a
important part
second.
is, oh, go ahead.
So basically, we're gonna do the parentheses first, then square it, and then add them all up once they're squared.
Correct. And I'll show
All
you
right.
that right here. So you remember, if you remember from algebra, order of operations, where the parentheses is really important, right? You want to do whatever's in the parentheses first, to Tyler's point. You square those values and then you add them up. And that's really important. You don't add them up and then square them. You square them and then add them up. Let me ask you a question. What if you were, okay, so let's say you have all, and this is going to be difficult, a difficult one. So put, if you don't get it, it's okay. Why would, exactly, Stuart, why would you square the difference first before adding them up? Why not just add them all up and then square them?
Might get rid of the negatives as well.
Bingo. Bingo. What would happen? Exactly. You have negatives. And what would essentially happen is everything would cancel each other out, right? Because if you have the mean, then half your values are on this side, half your values are on this side of the mean. And so if you take the difference, half of them are going to be negative and they're going to cancel out with the right. That's exactly right. So we square it first. We square that value to make sure that we're not canceling those values out. So you'll see that here. So let's say we have this little simple distribution, right? We've already calculated that the mean is 5. We know that's true. So this X bar is 5. So then what we essentially do is we take each value. So you'll notice the first value here is 5, right? 5 minus 5 is 0, and 0 squared is 0. Okay, so then that 0 comes here. Then let's move on to the next one. Next value in the distribution is 3. 3 minus 5 is negative 2. Negative 2 squared is 4. That's this value here. I'll just do one more. I think you get the point, right? All right, let me skip this one. We just did that one. The next value is 5. 0 squared is 0. And then we go to 6. 6 minus 5 is 1. 1 squared is 1. So you get the point. You see what we're doing? We're taking the difference, we're squaring it, and then we're adding it all up. And so what this is doing now is it's calculating essentially how far is the typical difference of each value from the mean squared to get rid of the negatives. And so we arrive at a value. When we do that, when we take that difference, we square it, and we add all those up in this distribution, you get to the number 83. And so 83 is what ends up at the top of this equation. That 83 is the sum of squared differences. That's basically what we would call it. Then all we have to do is divide that number by n minus 1, which is 14, because our sample size is 15. And so our variance becomes 5.93. And if you want to do it on the side after class or whatever, feel free to test it. That's basically what you would get to. So let's pause for a second. Becca, you have your hand up.
Yes, can you please explain why n minus 1?
Yes. So there's a couple of different reasons for that. Chris, feel free to chime in. There's a concept we're not going to go into a ton of detail on, it's sometimes called degrees of freedom. I'm going to try to give a simpler answer to this, which is if you were to take a population of data and you were to take a bunch of samples from it, let's say you had a population of data and you took 1,000 samples from it, and you knew what the population standard deviation was and the variance, right? Let's say you knew what that was, but you took sample after sample after sample after sample after sample after sample, and on and on and on. And each sample, you calculate a mean and a variance, and you calculate a mean and a variance, and you keep doing that. Well, what you'll find is sometimes that's called a Monte Carlo study or whatever it might be. You're just taking massive amounts of samples from a population and you calculate some value. Well, what happens when you do that, if you divide the number by the sample size, what happens is you tend to I can't remember if it's think you overestimate what the population variance is. So if you do that over and over again, what they found through all that is you get a better estimate of the population variance by taking n minus one. So that's the simplest answer to the question is through repeated trial, n minus one provides you a better estimate of what the population variance is. Chris, curious if you have a different.
Have you ever estimated something and you wanted to be a little safer? And so you like purposely moved the estimate a little bit? Like, man, I don't know how much I have in my checking account, but I'm not going to get the extra cheese just to be safe. You know, we've all had that moment. The minus one makes the denominator smaller, and when a smaller denominator, the variance gets bigger. So a bigger variant, it's essentially helping you err on the side of caution a little bit by making the variance or the standard deviation bigger.
Does that help? Does that make sense? Any other questions on this? Because I know this is hard to digest in a slide format. This is the kind of thing that helps with a whiteboard, and I'm not savvy enough to do that.
And now
Zoom.
we're going back to what we talked about yesterday about if your house is the average house, it's the mathematical center of all your friends. Everyone's got to drive to your house. Some are driving from the east, some are driving from the west, positive and negative. And if you want to figure out a distance, a measure for how far away, one number for how far away everybody is, that's what this is. And Becca, your question before about scaling it in a way to maintain the meaning of the numbers, kind of, but not really. There is a mathematical transformation that wouldn't square where we could get rid of the negatives. Does anybody know which that is from high school math? It's two brackets around a number. Absolute value, right? We don't use absolute value, and the reason we don't, and actually I can't get much deeper than this, so don't ask me any hard questions about it. The further you get away from the average, the bigger the number that gets. But when you square something, you get a parabolic increase, not a linear increase. So 1 squared is 1, 2 squared is 4, 9 squared is 81, right? So as you get further away from the mathematical mean, the variance actually gets bigger, right? And I can't tell you why that is, but it's different than doing an absolute value. So it's doing more than just getting rid of the negatives. It's also compounding as you get further away.
Okay, sorry, I was just answering a question there. Yes, that's actually a really good explanation for it. And there's a number of different ways to think about it, and I think I'm opting. There's a lot of different explanations for it, but I think that is a really good way to think about it. And the easiest way I think about it is if you were to do what Chris was describing, and if you have the mean in the center of the distribution and some of the values are lower and some are higher, you can't wash them out, right? You lose a lot of information when they cancel each other out. So you square it because you can always bring it back by taking the square root of it back to a value that makes sense in your distribution. Because if you think about it, these squared values are not particularly meaningful in relation to this distribution, right? Like 16, a variance or the difference of 16, that doesn't really make a whole lot of sense when we go back to the values of the distribution. The distributions are just ranging from 2 to 9. So why 16? Well, that's where the standard deviation comes into play. Once you square those values, you can always bring them back to the scale that you're working in. And that's the simplest way, at least for me, that I think of why we calculated this way, to make sure that the values don't cancel out, and knowing that we can always bring it back to the scale by square rooting it. And we'll get to that in a second.
I don't think I've ever used variance in a practical application. I've always used standard
I
deviation.
agree.
It's a
I
means
agree
to
with
an
that.
end, no pun intended.
Say that again.
I said variance is a means to an end, no pun intended. That's a
Oh,
good
it's a
one.
good nerd joke. I like that,
Yeah.
Chris.
That's a nerd joke and a dad joke all at once.
Nerdy dad joke. Even better. So so now the standard deviation, if you can conceptualize and you understand, okay, now I kind of see what we're doing here, right? You have a distribute, and we'll get to it in a visual in a minute. If you got values on the left side of the mean, you got values on the right side of the mean, you want to calculate what's the typical difference. The variance gets you there, but it's just not in a very understandable term. And so that's where the standard deviation comes in. And that word, or the word standard deviation, very meaningful, right? Because it literally means the standard deviation from the mean. That's literally what the term means, is what's your typical difference or deviation of values from the mean. And distributions and the normal distribution become very helpful. And we'll visualize that in 1 second. So to go through this process again, we calculate the variance, we go through that process, we take the sum of square differences, we take every value in the distribution, we subtract it from the mean, we square that value, and then we add them all up. And then we divide that by n minus 1. And that's what you see here. That's basically what we're doing here. And then to get to the standard deviation, super simple. We just square root that value. And that allows us to bring that value into the terms in a positive number, right? Because we lose the negatives when we square, brings it into a positive number that helps us explain the standard deviation of the values from the mean. And so what we end up doing is we do that calculation, the sum of squared differences. We add those values up. We divide by 14 and we get our variance of 5.93. And when we take the square root of that, 2.43. That is the standard deviation. So if you remember this distribution has a mean of 5 and a standard deviation of 2.43. Now let's visualize that in the distribution. So you remember this visual from yesterday, right? This was the standard normal distribution. Now we don't know for sure if this distribution is normal. That's okay. Doesn't matter for the purposes of this. But you remember that in the standard normal distribution, you have your x-axis. Those are the different values. That's where the 2 and the 3 and the 4 and the 5 all the way to 9 would fall. And then the y-axis is how often you see those values show up. So let's assume this is the visual, right? We know that our mean is 5. We've already calculated that. We also calculated yesterday that the median is 5. We know that the mode is 3. 3 is the most common value in the distribution. The range is 7, ranges from 2 to 9. 9 minus 2 is 7. We know that the variance is 5.93, but again, that's not super meaningful to us. That doesn't make a whole lot of sense to us mentally, but this number sure does. And what we can calculate now, very simply, is that this, and again, this is difficult this value here, 0, would basically be 5. This number here, where one standard deviation above the mean, any guesses what that value would be? If this is 5, what would this be?
7.43.
7.43. Exactly. Now this is tougher because you got to do the tough subtraction. But this would be 5 minus 2.43, which is whatever that is. I can't do that in my head. So let me pause there. Is that starting to kind of make sense? What we're doing with these distributions and these values? Is that starting to jive? Any questions? Because we're going to do a couple of exercises to kind of work through this in a minute. But any questions on the variance or the standard deviation? And there's no dumb questions here. Feel free. Making sense? Okay. Okay, so these are gonna get a little tough. They might be really easy, might be a little tough. I don't know. It's hard to say. let's do it as a group real quick because we don't have a ton of time. So in this distribution, right, keeping in mind these values, let me take a screenshot. Let me just put this in the chat so we can go back to our distribution really quick. Give me 1 second. Um, oh, dang. Is it not? Okay, sorry, 1 second.
Ben, do you need some help with breakout rooms?
No, I was just trying to, thank you though, Brittany. I was just trying to put this here
Oh,
in the chat so we can focus on this while we're playing around with,
got it.
oh, Bailey, go ahead.
Just real quick, so would we, for the standard deviation, would we say that it's plus or minus 2.43 from the mean or median or mode?
Just the mean.
Just the
Good
mean. So
question.
it could be plus or minus. Okay. I was just making sure that's where that fit in. the
Good
plus or
question.
minus.
Good question. So we can't say that it's 2.43 away from the mode. It happens to be that from the median. But if you recall, when we calculated the variance and the standard deviation, we were using the mean.
The mean. Right.
Right. Right.
And mathematically, that is the case. So even if you have skew in a data set, the standard deviation is plus or minus from the mean. Now, what percentage of your data points fall within plus or minus 1 isn't reliable unless you have a normal distribution. But mathematically, the plus or minus verbiage is giving a good idea of where values are floating, right? And unless you have a data set that doesn't have any kind of curve at all, it's usually a pretty decent indicator, even in skewed data sets, of around where your stuff is floating.
Yep.
Tyler.
So then, in a positive or negative skewed data set, would we use then the median as the starting point? And then once we find the standard deviation, still using the mean. Sorry, my dog is getting upset.
Good
Still using the mean
question.
to figure out the standard deviation. Using the median, is that where we would see that 2.43 moving from there, or no? Because it's a skewed data set, it doesn't have that ability.
Okay, I think I understand what you're saying. So we talked and sorry, I'm gonna back up a bit. I think what I'm hearing you say, Tyler, is we've talked about like in a skewed distribution, sometimes you're better off using the median because the means really affect it, right? So if the question is, what's the center of the distribution in a skewed distribution, normally it's not the mean. However, when we are calculating and talking about the dispersion or the variance or the standard deviation, we're talking about that value in relation to the mean, even in a skewed distribution. So, meaning if you are going to describe the center of a distribution to somebody who doesn't know anything about statistics, and it was a really skewed distribution, you would probably use, and it kind of depends on the scenario. There's no like one right way to do that, but you would probably use the median to describe that. However, if they then asked, well, how far do they typically vary from each other? Like what's the, and they're asking a general question about what's the standard deviation, you still have to calculate the mean and you have to interpret the standard deviation in relation to the mean, not the median.
A way that might be helpful to think about it is we talked about how the mean is not robust to outliers, which makes it dangerous to use as typical. But what the mean is a mathematical center point. It is a mathematical center point, whereas a median is more of a logical center point, right? The median is the 50th percentile. Half the scores fall above, half the scores fall below. And so that has a lot of utility when you're trying to describe typical. Mean is a mathematical center point that has a lot of application for calculating things like standard deviation and other things. So you're always going to use the mean when you're calculating standard deviation. And if you think about your data like a cloud, right? The mean is the middle of the cloud, but the standard deviation defines how dense the cloud is. Very high standard deviation, very not dense cloud. Very low standard deviation, very concentrated, dense cloud.
That's a really good question, Tyler, though. That
Yeah.
that is a really good question because that does get kind of confusing. Yeah. Okay, so somebody threw it in there. So in this distribution, we would expect 68% of the values to fall between what values? You can type it in or yell it out. 68% will fall between 2.57 and 7.43. How do you know that, Becca?
So the 68% is within one standard deviation to the right and to the left of the mean. So you just we subtract the standard deviation from the mean for the low end of it, and then you add standard deviation to the mean for the higher end of it.
Spot on. Well done. Excellent. And you're right, exactly right, Bailey. You're just using the standard deviation and you're calculating one standard deviation. Now, here's a little tougher one. In this distribution, it's a very simple distribution we have. I'll go back to it. We would expect about 2.2% of values to be above what value? So a little tougher. Bingo. And explain that. How do you know that it's 9.86? What did you do?
So it's kind of hard for me to see, but I think that the upper two ranges, the 2 and 3 standard deviation line, that adds up to 2.2. I think so. Basically, is I just added the standard deviation twice to the mean to get to that.
Exactly. Exactly. So all you're doing really is each standard deviation, each iteration of 2.43, you're just adding 2.43, add 2.43, add 2.43, subtract 2.43, subtract 2.43, subtract 2.43. And that's how you get, that's where the standard deviation comes in and it shows you, the percentage of the values that fall between that. Because again, we know in a standard normal distribution, how many percent, what percentage of the values fall within certain values are standard deviations from the mean. Exactly. So is that kind of jiving? Does that make sense so far to everybody? Okay.
You've seen this even if you don't realize it in standardized tests that you've been taking your whole life. When you get that percentage, you scored higher than 75% of other test takers. You scored higher than 80% of test takers, right? They've engineered those tests to fall onto a curve like this. They have a standard deviation against that normal score. And then we can say SAT average is 1,000, standard deviation is 150. If you scored 1150 or you scored 1300 or you scored 1450, that puts you in progressively more exclusive classes of test taker, right? That's exactly how these kinds of numbers have application in day-to-day life. They're often used for normalization of scores so that you can bucket people into achievement classes on things like tests. Or
Bingo.
vision. If you've ever taken a vision test and told your vision is better than 95% of people, this is the math they're using to figure that out.
Yep. On vision, I'm way down here for the record. Got a lot of correction. Yeah, that one, this third question was more of how could you simplify the terminology? We'll skip that one for now because we don't have a ton of time and it's kind of a little bit off the point of what we're talking about. So this is kind of the answer key for those questions. But yeah, you all got them exactly right. So we know that 68% of the values fall within 2.57 and 7.43. And that's quite easy to calculate because now that we have our mean and we have our standard deviation, we're just working with those numbers and you just keep adding this way and you keep subtracting this way. And it's relatively straightforward. And then you can also apply that, as Chris was saying, to calculate if you know a certain value, like if we said the value 7.5, and what percentage of values in the distribution are above 7.5? That's actually relatively simple to calculate. We won't do that here right now, but that's a pretty simple thing to calculate because we have all the information we need to do that.
Then I'm really glad you put it that way because that's a really practical lesson here, right? Because whenever somebody says, is that good or is that bad? Your first question as a consultant should always be compared to what, right? And typically it's compared to some amount of other data. So if we pretend these 15 numbers were scores on an engagement survey and we say Jasmine got a score of 7.5, we could then, if somebody said, did Jasmine get a good score? We say, well, what data do we have? Okay, we have these other 15 numbers. Well, it looks like if she scored a 7.5, she's about a standard deviation above the mean. So she's not blowing the doors off, but she's doing better than, more than 68% of people, actually more than 75% of people, right? Because she gets
Right.
she's above the whole distribution below her, right? So when somebody says, is that good or is that bad? The answer is always compared to what? And go back to the frequency distribution because that's what's going to give you the answer.
That's a great point. And so you could do that really with anything. And any value in a distribution, you could plug it in and say, okay, what about 8? Is 8 good? Well, 8 would be pretty darn good because 8 minus 5 is 3. And 3 is higher than 1 standard deviation. So you're looking at somewhere right here as a value of 8. Yeah, that's pretty good. That's higher than a large majority of the rest of the population. Is a score of 1.3. That's pretty obvious one. No, it's not because that's several standard deviations below the mean. Now, you might recall, we're going to talk about this next week, that magical number of 0.05, right? That 0.05 number. P less than 0.05 or alpha equals 0.05. We're not going to get into all the details. The associated value with that you remember from the sampling exercise was 95% confidence. And if you recall, 95% of our values fall within these 2 standard deviations, right? So only 2.2% fall in those extreme tails each. Add those up, that's about 5. That's where that magic number of 95% confidence and 0.05 that alpha of 0.05 come from. And so generally speaking, the way I'll use that to combine it with what Chris was explaining is in organizational research, typically, if we want to know if this score was high or low or statistically significant, what we're basically doing is we're determining whether it was 2 or more standard deviations above the mean. That's typically what we're doing. And that means that the probability that that value we found falls into this distribution, if it's that high or it's that low, the probability is low. And it's lower than 0.05. And so we conclude that it's statistically significant. So I'm teeing that up now, not as something you got to memorize now, but I'm teeing that up now because we're going to talk about that next week. And I want that to click when we get to it next week.
I also want it to tie back to all the argumentation we've been doing. Because when we said Jasmine got that score of 7.5, is that good? We said compared to what? And then we said 7.5 is a standard deviation above the mean. That means she scored higher than 84% of people. What do we just do? We just created an operational definition for what good means. We said, well, if you customer think scoring higher than 84% of test takers or 84% of sales reps on this test is good, then yeah, Jasmine did good or did well, right? So when you start to take plain speech like, is that good? And you start applying numbers to it here, you're then saying, I'm not saying good or bad. What I'm saying is, of all the people that took this test or got this survey back, Jasmine scored higher than 84%. So yeah, I would interpret that as good. But you're not necessarily making a judgment. You're just backing up the verb or the adjective good with a number that most people that are reasonable would agree is good because it's better than
Yeah,
84% of people.
I love that explanation. Bailey.
And just to clarify, Chris, what you're saying, so that would look different depending on the distribution scale, right? Like if it's positive or negative, like that's referring to an equal one, because obviously if it's negative, or I'm sorry, positive. No, yeah, if it's like negative and she's like technically above the mean, but it's still bad
I
grade.
love how you're thinking about that, Bailey.
Okay.
You're scratching at the reason distributions are so important. And I'm so glad you're thinking about it that way. Because if this distribution was negatively skewed instead of normally skewed, maybe a 7.5 isn't that great. Maybe a 7.5 is a whole lot closer to typical, right? But in that case, if it wasn't normally distributed, we wouldn't simply be using the standard deviation to define it. We'd have to look at what if maybe a percentile rank of how Jasmine scored, right? Because if the data was negatively skewed, then simply being one standard deviation above the mean might not mean what it does in a normal distribution. This
Right.
is why understanding your distributions are so critical to assigning value or judgment to what an individual score is. Because an
Right.
individual score only has meaning relative to the other scores in the distribution. And to understand that, you got to understand the mean and the median and the mode and the standard deviation.
Tyler.
So you mentioned it earlier, but is this why you would take a lot of samples to where if you see a bunch of negative scores or a bunch of positive scores, like let's say on employee engagement and like an employee feedback survey, and you see a whole bunch of like weird skewed data, you would still want to take more samples? Is that why? To be able to shape out the actual distribution?
Um, that's a tough one. Trying to figure out how to answer that. I The way I might answer that, Tyler, and forgive me if I don't answer your question directly, is we the larger the sample size, I'm going to take it in the sample size direction because normally, like I was using a lot of hypothetical examples of, oh, you take a bunch of samples from a population and then you look at all of them individually. That typically is not what we do in organizational research. We usually get one, maybe two shots at a sample. Or if, like in your case, if in your example, if we're surveying a population, we might get a few samples from it, but we're normally not taking repeated samples from it. That's more of an academic exercise to explain why we're doing what we're doing. But we what you would do, the sample size, right? So here's where I might take it. Let's say we had a big population of data that we know was normally distributed, but you took a super small sample from it. The chances of that super small sample being representative is much lower than a big sample. And the shape of that small sample distribution might be really wonky. It might look all over the place because it's just small. It doesn't have the number, the sample size to mimic what the normal distribution of the population looks like. So a larger sample size is going to be much more likely to be representative of the values in the distribution. Same thing we were talking about in the last couple of weeks with sampling. Imagine in this distribution, you have people of white skin, brown skin, black skin, you have women, men, you have kids, you have adults. The big sample is picking up all the is more likely that it's picking up all those different values, and it's finding the extreme values in the distribution is finding a lot of volume in the middle of the distribution. So you're more likely to get a representative sample as you increase the sample size. my stab at answering your question.
Sorry, and then it was the Monte Carlo study that you said where you do like you take multiples. Why would someone want to do that?
If you're a real nerd like me and Chris, no,
I'll just leave it.
there's a variety of reasons. I don't know, Chris, you might be better at answering that one, or
Um,
bootstrapping or whatever.
Yeah, when you're doing like serious data science and algorithm development, there are reasons to take lots of different samples. It's often to boost the power of your model, and unfortunately, we just don't have time to go down that route. I'm happy to talk to you about that offline if you want. But I did want to triangulate what Ben said because depending on where you go with the IO work that you're doing, if you're if you're in a scientific role where you're looking to find effects, you're going to be spending a lot of time understanding samples, trying to create good samples so that you can get representative views of your population to see effect sizes. If you go in a direction where you're in an internal role and you're attacking organizational problems, you're far more likely to be working with populations more often. Now, your population might feel like a sample because you're looking at this group that got a treatment condition and this group that didn't, but now you're not really inferring, you're just looking at how populations are behaving next to one another or within each other over time. Um, and so you're not really trying to do a lot of sampling to create a normal distribution, Tyler. You're really trying to understand the nature of the variable and whether the variable is normally distributed. Most naturally occurring variables are normally distributed. However, things like floor effects, ceiling effects, range restrictions, sample size, there are all kinds of things that will make a sample or a population fundamentally not normally distributed. So you're not trying to combat that so much as you're just trying to understand the data for what it is, right? If you try to change your partner, you're probably not going to have a great relationship. You got to understand who they are and love them for they are. Data is the same. You're really just trying to uncover its characteristics so that you know what's going to work and not going to work with the problem that you're trying to solve with it.
Yep. Great questions. Okay. So let's move on a little bit. We're just about done with the lecture and then we'll move into the exercise. So oh yeah, we just talked about that last. This is just a quick summary of the values. Nice little cheat sheet if you want to take a quick screenshot, but we'll post this. This will be available to you. I'll give you a second. And then one more quick concept that relates to what we've been talking about that is also extremely valuable is what's called a Z-score. And it's, again, another fancy term, looks like a fancy, complicated formula, but it's actually quite simple once you understand what we just talked about. And so a Z-score is what we use sometimes to help us calculate the probability of a score occurring in a normal distribution. And yeah, it's a super valuable tool. I actually, we use it all the time at Qualtrics. Some of our technology calculates Z-scores automatically, and it helps kind of what Chris was explaining earlier, that relative nature of the score. Is the score good? Well, Z-score helps to answer that. And so it's also really helpful too, and I'm going to use this as an example when you're comparing two or more scores from different distributions that have different means and standard deviations. So trying to think, I think I have an example on the next slide. I won't spoil it yet. But basically, all we're doing in a Z-score is we're taking the value that we're interested in, whatever value that we're trying to test, or we want to know, hey, is that a high score? Is that a low score? Is that good? Is that bad? It's exactly what we just did, in fact. We subtracted from, and this is just in population terms, this could be X bar or mu, whatever, the mean. How big is that difference from the mean divided by the standard deviation? So all we're doing here is we're calculating the ratio of how different that value is from the mean to what's normal, what's the standard deviation. That's literally all we're doing. And then that tells us, is that a low score? Is that a high score relative to the mean and the standard deviation? And so really simple example here. If we wanted to know what would be the Z-score for a value of 2 in this distribution, super simple. We take that value 2, subtract subtracted from the mean, which is 5. And then we divide it by the standard deviation, and we arrive at a z-score of negative 1.2. And what I love about z-scores is that they are interpreted in terms of standard deviations. So this means basically that the value of 2 is 1.2 standard deviations below the mean. Simple, easy peasy.
It is very, 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 very useful when you're comparing the same metric in different groups with different baselines. I'll pick on Chelsea because she's in the consumer product good distribution space. And if I am a sales rep in Oklahoma selling Tito's and I'm a sales rep in New York selling Tito's, the sales rep in New York compared to the sales rep in Tacoma or Topeka is always going to look better. They're always going to look like they're the better rep because they sell more, because they have more traffic or they have bigger accounts. But if you take a z-score of all of the Topeka reps and all the New York reps, now the distributions all have an average of 0 and they all have a standard deviation of 1. And so even though I might sell more Tito's overall in New York, that doesn't necessarily make me a higher performing rep relative to where I live or relative to where I'm selling the product, right? So this is really useful when you're trying to understand performance and you have constraints like different markets or different levels or different job codes that are going to influence and skew your data in an unfair kind of way. And in chapter 13 of the book, which I think has been assigned at this point, if I remember, there's an exercise that explains that exact thing with real numbers and real examples. But it's an incredibly useful way to normalize, which is the term for transforming data into a way that's more useful or explainable, when you have different baselines on the same metric.
Exactly. And Chris used a different example. I have one here, but and this is just from my world of survey data, where it's very common when we do global survey work to find that the distribution of survey scores across different countries looks wildly different. And this is largely due to cultural differences in how people respond to questions. And a classic example, and this is true, we see this in our data, is when we do research of people, employees in Japan, and we compare it to, let's say, American employees or Canadian employees or whatever, what you tend to find is that Japanese people, for cultural reasons, tend not to respond at a high rate to the extreme ends of the distribution. They tend to be kind of in the middle. So if you had a 5-point scale of your survey and 1 was real low and 5 was real high, Japanese people are more likely to be in the 3 middle ranges. So there's average score of Japanese people on a survey might look lower or maybe a little higher than Americans, depending on what you're asking. But the variance and the standard deviation are going to be a lot tighter for the Japanese than they are for the Americans. And so what often happens is when we run these types of surveys for companies, we'll report out on the raw scores like, hey, the Americans, they're 76% engaged and the Japanese are all 50%. Oh no, what's going on in Japan? Nothing's going on in Japan. And that's just normal for how Japanese people respond to surveys. And we can use these scores to compare what is 50% engagement in the Japanese region. How does that compare to 76% in the American region? And it might be really close. They might be really close when we transform the data into z-scores. So it's a really good example. It's just another one very similar to what Chris offered. When you have different groups that have different means and different variances, different distributions essentially, and you're wanting to compare them in relative terms, the z-score transformation is extremely helpful and is super stinking easy. Okay, so I just want to look at Bailey's question. So New York and Japan, you can have 2 different numbers for sales or whatever, but the z-scores can both. Yeah, that's correct. That's technically possible. You could have a value of the raw number value could look totally different, but the z-score value could be exactly the same, depending on, that's a very possible scenario, Bailey. Exactly. Any final thoughts, Chris, on this one?
Yeah, I was just going to say that the example in the book, if you want to look it up, we have to move on for now, but it shows an example of one sales rep who sells more dollars, but has a lower Z-score than their peer because their peer works in a different geography, right? And so one makes more money or has created more revenue for the company, but the other rep is actually a higher performing rep based on where they are once you control for where they are. And so you can see this really in action with a real example if you look in the text.
Okay.
And this is also, by the way, used for things like setting commissions and bonuses, right? If you go and live in Topeka, you don't have to sell as much to hit the bonuses, right? And a lot of that is done with these sorts of descriptive examples.
Okay. Well, that's it for our lecture on descriptives. Hopefully that kind of demystifies some of this for you and starting to kind of make, and we can tell just by the nature of the questions you're asking that this is coming together. So I guess with that, Chris, do we want to move to kind of introducing the final project data sets and kind of diving in? How do you want to handle that?
Yeah. So Dr. Ben and I are trying to recreate a scenario that we lived through in grad school where most computer labs would have a bunch of like desks with actual, not laptops, but like desktops because we're that old. And the monitors were all facing the wall. And we all sat with our backs to the middle of the room and had to do our stats practice. And our professor would just kind of walk in a counterclockwise or clockwise circle, looking over our shoulders, or we would turn around and raise our hand when we got stuck. So that's kind of what we're going to approximate here tonight. The video that you all saw, I hope you guys watched it and you have the stats package enabled on your Excel. You should also have the Excel document or the Excel workbook downloaded as well as the Word document. And what we're going to do is we're just going to work through recreating the workbook that I created in the video. And you're going to answer the discussion questions in the Word document. So what does that mean from a hand-in assignment perspective? Those are the two things when they're done, you're going to upload on Saturday. But for the next 50 minutes, we're going to be in this group setting and I'm going to have you all do the assignment. Use the video as your instruction guide. And Dr. Ben and I are here. And if you have a question, raise your hand. You guys can stay on camera, go off camera, whatever you want. But if you have a question, come on camera, raise your hand, and we'll answer it. You can screen share. I can screen share if we need to. And the whole class can kind of get the betterment if you want to listen in on any questions that you guys have. We wanted to have a real kind of moment where y'all can get your hands dirty with data, but that we're here to get your back. And then on Saturday is when you're going to hand this in as a final assignment. Becca.
I think I accidentally went ahead and I already did it. So would a good step be to try and maybe do it without the video to see how far I get?
Sure. Yeah. And if you've already built it, if you've already done it and it looks the same way, because what I would say is we don't have a formal instructional guide here. You're going to have to go back and see, did I create all the right tabs? Did I put all the right data in those tabs? Right? Because there's no answer key like there was for the data manipulation. I'm just looking for you to create these data. Because spoiler alert, we're going to do a similar one next week. And then you'll have these two workbooks with different visuals in them that you've created. And that's what you're going to use as ingredients to create your final project. Right? So right now you're creating the ingredients for the presentation you're going to give. Make sense? I'm seeing nods.
Yep.
Cool.
So if we
Oh, go ahead. Go ahead.
So if we followed along with your video, we've already done the assignment that we're trying to do this weekend.
Yes.
Okay.
Exactly.
Correct.
And so you have the next 51 minutes to ask Dr. Ben and I questions about this. And then between now and Saturday to tighten it up and get it to where you want it to hand it in. And then we'll be grading it as I think it's a lab assignment.
And And Chris, there was just a question I want to make sure I'm answering correctly from Marina in the chat.
So both. So the Excel
Yeah.
worksheet you have to hand, or the Excel workbook you have to hand in replicated based on what was in the video. And then I also want you all to answer the discussion questions. So you don't have to answer the discussion questions exactly how I have them written. And I mean, the answers are there. You can see them in the video. But I want you guys to go and put your own brain power on it and put it in your own words. This is in addition to the fact that you have to use this vignette, right? And do the vignette assignment with this vignette. So the verbiage that's in the Word document in the video is also in your vignette assignment, so that you can also break down an argument, do the logical premises, etc., etc. So you've got the vignette assignment, that's still the vignette assignment. You got to answer the discussion questions, and you got to reproduce the workbook. Cool?
Cool. All right,
Will
we'll hang out.
will this recording be posted before Saturday in case like someone else asks a question and we go back later?
Yes.
Okay.
We need to give a thumbs up. so
Yeah,
that
I'm
sounds like a
gonna, I'm gonna handle that. I'm gonna get the recordings from last night's class and tonight's class uploaded and into the Canvas by tomorrow.
Perfect, thank you.
You're welcome.
Cool.
Great.
Okay. Well, feel free to chime in at any point. Feel free to chat. Go stay on video, go off video, whatever you prefer.
We'll be here.
They have to pay
I'm gonna read papers. That's what I'm gonna
all of it.
I think we should stop the recording maybe.
Well, I think
Just
that's
since
what
it's-
Ashley was asking, like
so
if there were
What
questions.
happens?
Well,
We
we
might
can
wanna-
turn the recording on if somebody asks questions, I guess, right?
Yeah.
Okay, just let it keep running and then people can
Yeah,
watch
sorry, that might
if there are any questions.
Yeah, that might we may not, you might just, if you're watching it, the video later, you might just have big lags. I'd hate for Brittany to have to edit this one without the
Right.
silence.
So we
Yeah,
can
that's
we can
that's what
pause it.
takes so long, is the editing. So if
Yeah.
I cannot edit, that would be best.
That's
So
cool
let's
with
pause
everybody.
it, and if we have a question, let's just make sure we
Okay.
unpause.
Sure that they know. Number two.
Cool.
troubles actually knowing what the data is, like what I'm reading. So would I, for question number 2, we're being asked if Jack was right. So would I use the average to determine if he's correct? I know you said it in your video, but I want to answer these questions like without you. Oh, I can't hear you.
What data and or visuals did you look at to try to deduce whether Jack is correct or not?
Yeah, okay, so let me pull it
You
up.
want to
So
screen share? Why don't you screen share? Can we
Okay.
enable that?
let me see. Hopefully it lets me. I always have issues with this. Share screen. Okay, can you see?
Yes.
Okay, cool. So I was looking here. So I was like, okay, the mean. And then, but what I was originally looking at was the graphs.
Okay.
And I was looking at like the West is consistently experiencing higher turnovers than the other regions.
Mm-hmm.
Yeah, so, but am I on the right track here?
You are on the right track. So
Okay.
you're seeing 2 different graphs here.
Yeah.
What are these graphs telling you?
So from what I understand, this is letting me know like the month for, so like April 2023, May 2023, like what the turnover was looking like for these months.
Mm-hmm.
And then here it's broken down for me in like percentages, like what those are looking like for each region.
Correct. I might refine the words a little, and I know I use turnover exclusively in the video. That was on purpose. But for the sake of now that we're getting to the solving part, I might
Yeah.
call the top one a measurement of terminations, and I
Okay.
would call the bottom one a turnover or turnover rate.
What was that first term you used?
Terminations.
Oh,
So
okay.
this is a personal style thing. You'll find this used interchangeably in the industry. But when I
Okay.
use the word termination, I'm talking about an action. If Ben worked for us yesterday and not tomorrow, he was terminated. That is a termination that shows up as a record in the data set. turnover is terminations divided by a headcount measure over a period of time. How many
Gotcha.
terminations happened in April? X number, right? In the West, it was 716 in April, right? But the turnover rate was 3.15% because there was an average of 22,697 employees in April.
Mhm. Okay.
So if we're asking Jack, what were Jack's premises and stance about why he thought the West was the problem?
From what I remember reading, it was because that was the didn't something move over to the West Coast? And then they started
Well,
experiencing all
yeah, bring
like
the vignette back up. Bring the vignette back up and look at exactly what he said. He made some pretty damning.
Can you still see my screen, by the way?
What's that?
Can you still see my screen?
Yes.
Because I'm on it right now. Okay, just making sure.
Oh, we're seeing the Excel.
Yeah, we're still seeing the
Oh, you're in the
turnover
Excel?
pivot.
Okay, let me try to see because I'm on here right now. Let me see if I could change.
If you share your whole screen instead of just
Yeah,
the
I can do
Excel.
that. Let me see. Let's see, hold on. Okay, cool. That should have worked. Can you see it now?
Yes.
Okay, cool.
So Jack says, well, I'm not saying I have a solution, or Jack is saying, I know what the problem is. The problem is the West. We never had
Yeah.
these problems before. We expanded into the Pacific time zone, and it's been nothing but trouble ever since. And then at the bottom, he says, I'm telling you, it's the West. They turn over more than any other region. I've seen the numbers. So based on that, which numbers do you think he's seen? Based on what you have in the Excel document.
Here's where I'm having the issue. I would think he's talking about these numbers.
Well, what is that a mean of?
Is it the weeks of like termination or whatever?
You're getting there. What does TAT stand for?
I'm blanking. Turnover something.
Tenure at termination.
Oh, yes.
So these data are about when people are quitting. This data set is more concerned with answering the question about when people leave that the CHRO is asking.
Yeah.
Whereas this is more concerned about who has more turnover across time. And so they're kind of
Would he
these.
be looking at this? Or I mean, this.
Yeah, I would argue that that's probably what Jack is thinking. Jack is thinking about which geography has more people walking out the door, which is a
Yeah.
very legitimate cost pressure to any business. However, we're not talking about how many people are walking out the door in this vignette. We're talking about, or we're accusing, right? That's what Jack's doing. He's accusing this group of being worse at turnover than the other regions. And while that may be objectively true if you look at how many people quit, when you're talking about a behaviorally based phenomenon like turnover, you have to consider the things that are controllable and not controllable by an organization. And your general size is going to influence how many people leave. And so you kind of have to control for that if you're going to really provide a thorough answer to the question. So it wouldn't really be fair to report just the number of terminations without also recognizing the fact that the West is the largest group of the three.
Right. Okay, cool.
So when considering that,
So technically he is right, but like because it is, but he's not taking into account how big the region is. So of course there's going to be okay. Am I on the right
Yeah,
track?
that's
exactly.
right.
Okay.
Exactly.
So like,
Yep.
how would I answer that though? Technically he's right, but and then like give you the rest of that.
Yeah, welcome to being a
Don't be
real
nice to Jack.
consultant.
Jack, you are wrong, man. No, I'm kidding.
I'm like, technically you're right, but you're not taking into consideration like how big the West Coast is.
I've been doing this work for about 20 years, And I can count on one hand the number of times a business leader or an HRBP has been flat out wrong. It almost never happens.
Okay.
They almost always have at least a point that's valid, but that doesn't mean that the conclusion they're drawing from their premise
Mhm.
is valid. Jack is saying there is a problem with turnover. That's his conclusion. And his premise is that they have more terminations than anybody else. But that's not actually a valid conclusion from the premise when you consider the fact that the West is bigger than everyone else. So what you're bringing to the table, if we think about this from an argumentation perspective, is Jack, 100%. They have 20% more terminations every month, but they also have 20% more employees. So you need to pump your brakes on saying the West has a turnover problem until you understand the overall size. I wouldn't suggest you say it exactly that way to Jack. But you
Okay, so
guys are
like Jack,
following
you're wrong. If you
well, the
Jack?
point that we're trying to make here is that, Jack, your observation of the data was correct, but it was also incomplete, and that invalidated your conclusion. So when we
Oh
go
my
and make
gosh.
this case back to the CHRO, we can say, look, Jack has a point. If we're talking about straight cost pressure, the people walking out the door, if it costs $2,000 every time someone walks out the door, the West is costing the business more money than anybody else. But that doesn't mean they have a culture problem or a manager problem, because they're not turning over at a higher rate.
Right.
So if we want to go remediate the turnover problem, it's not about fixing the West. It might be about giving the West some more love in other ways
Mm,
to control for the fact that they have a cost pressure that nobody else has to deal with because of their relative size.
right. Okay, cool. All right. That's super helpful, Chris. Thank you so much.
Sure.
Just going in, you mentioned when you're explaining the breakdown of like the mean, standard error, median, and mode, you mentioned in the count that that's a total of tenure over the 3 months. I'm not sure where that came from because I don't remember seeing that in the data or the
In the data table that gets created, the descriptives table.
Huh?
You want to share your screen? I think what you're referencing is a total number of terminations in the quarter, but I want to see what you mean if you can share screens.
So at this point, you mentioned 3 months
Right.
in the video. So I'm wondering where the 3 months came from. Like, where does this data come from?
So that data was created from the tab of the Q2 terms report.
Uh-huh.
Right.
Oh,
So
no.
so if you look at the oh, you're paused on my video. I got it. This is weird. Right. So the Q2 terms report, go to if
Here,
you
I'll
read
share. I'll
if
share
you
my.
rewind a small amount, it'll bounce over to slide 6. Oh,
Let me just share my. So with this one. Is this it? Okay.
so
So
that I'm
yeah.
seeing the video again. Is everybody else or just me?
No, I think this is the. Do you see?
I think I see the video screen.
I don't know why it's not showing.
I can open up the Excel and share if you want.
Okay.
That might be helpful. It's opening. Hang on. Let's bring the video people up here and then open this bad boy up and then save that and then screen share. And then we're gonna say this screen. You all seeing the Excel sheet?
Mm-hmm.
If the skew is less or the peak is low, we can infer that low tenure is likely the cause for increased attrition. Again, that's not me, is it? None of this. I mean, it is me, but it's not me. Triangulating correlations to
No,
create
I think it's Mallory.
preponderance of evidence is a legal definition for when. Gosh, how do you guys listen to us for hours? All right, so you were referencing, Julie, I think this table, right? Are you guys
Yeah.
seeing my screen still? Got it. So if you go backwards into the video, essentially we take these fields, the
Right.
turnover weeks, right? And we transform it into this more statistical kind of look, right?
Yep.
And then that is where these data, after we've sort of normalized it for all the 3 months of 3 months of turnover for the Midwest, 3 months of turnover for Corp, 3 months of turnover for Northeast, for South, and for West, that's what produces this. So these data are the descriptive statistics about 3 months of turnover broken out by region. And the kind of the light data engineering we do in the middle of the video is producing these variables across the 3 months to create this. So what you're seeing here in count is the amount of terminations, the amount of observations, basically, of terminations in each of these groups over the course of the time period. Is that helpful?
Which is 3 months. And Mike, I guess just to clarify my question, I was just wondering where you got the 3 months
Ah,
from,
so
like the higher, like where did you get that?
so I have it because I know how much data is in here because I built it. But if you wanted to test it and say, well, how much data is in here, right? You could take a look by doing this, right? You could say, I know I've got 423, 523, and 623. Got 3 months of data in here.
Excuse me, Chris, can you take it back a step? How you made that month one?
How I made this?
Yes, from the term date, because we're most likely going to have the term date of an employee. We're not going to already have it like in that beautiful column. Thank you, by the way.
Yeah. So I did this just trying to save you guys some data engineering work. But essentially, this nifty thing you can do with any kind of date field is you can grab any piece of it with a very simple piece of logic. So I said equal month of this term date, and that gives me the 4, and then equal month or equal, sorry, year of this term date, right? And now I've got a 4 and a 23. And then if you guys remember from our original, right? Concatenate this with an underscore and then a this, and now I've got a 423. Is that helpful, Tyler?
You know it was, Chris. That was beautiful.
Yeah. One of the things I'll warn you about here, just be careful, is when you're doing things like months, you got to make sure that I would actually suggest that you use a leading 0 here, because if I got to like October or November, then my 10, 11, and 12 would come up with my 1. They wouldn't go at the bottom. But if you use 0, 1, 0, 2, 0, 4, right? And the way you could do that is you could just put an extra argument in here and put a 0, right? I didn't do it for this exercise, but I would suggest it, right? So now you have 0, 4, 23, and just make sure that you always use 2 digits for your month because it'll just make it sort easier.
Can you drop that logic in AL? Yes.
Yeah. I can drop it here. It'll also be in the recording so you can take a look at it. But yeah, so there you go. Cool. Any other questions on this? We've only got about 9 minutes left. So if you guys have questions, now is the time. All right, T minus 9 minutes. We'll be here. There we go. Okay. So I'm trying to think of how to explain this simply. Her hypothesis, so Jack's hypothesis is that it's the West's fault, right? The West is the problem. And as we talked about with Jasmine's answer, well, yeah, the West has more turnover, but they also have more heads. So they're not really driving more turnover relative to their size. Sandra's hypothesis is that people with lower tenure tend to turn over more. So if we have more people with lower tenure, we're going to have more turnover. Does that track? Okay. So in these data that we have here, we can't really see it the way we see it with the West, because in the West, we can compare the West to the other regions and we have a comparison group. In these data, we don't really have anything to compare this to, right? We'd have to go find other times where we had hired fewer people and see if we had commensurately lower turnover. We can safely assume that if this distribution continued to look this way, that lower hiring would mean lower tenure people, and then this bump would be lower and we'd have less turnover overall. But we can't really prove that. However, Jack's definition of turnover was actually termination count, not turnover. And so him being right was contingent on whether we were talking about terminations as a raw amount or turnover as a rate that controls for some amount of headcount. Sandra's definition doesn't really rely on the same premise, right? She's just saying when we have more people with low tenure, we're going to have more turnover in general. And therefore, if we wanted to do more investigation here, we would have to go digging for other periods of time that looked similar or different to this with regard to distribution of headcount, right? And then take a look at what turnover looked like when those hiring numbers and headcount distributions were the way that they were. The other thing we don't have in these data is a roster of active employees. One of the things I've done before is you compare this curve to the curve of your active roster. And you can see that, does the curve of my active roster look like the tenure curve of my active roster look like the tenure curve of the people quitting? Right? And that can be very telling if you're comparing the distributions of what's the general age of tenure in my company compared to what's the general age of the people that are leaving. I don't mean physical age, I mean tenure, right?
Like a sample size, in a way, like you're looking at a sample of terms of a turnover.
There are two populations. You have your population of people that quit, and you have your population of people that are with you. But if the people that are leaving your company all have something in common, then that might be something interesting, right? A few years ago at a different company that I worked at, we discovered that we had a lot of employees entering retirement age and retirement eligibility. And so we had this uncommon bump in our turnover for very high tenured people, right? And it was creating knowledge management pressure. It was creating all kinds of worries because a lot of intellectual property and experience was walking out the door, right? But when you looked at those two curves, you could see very clearly that there was a bump where there shouldn't have been a bump, and there had never been a bump there before. But it was because of the way that the population happened to be aging and all kinds of other things that were kind of driving this unusual bump in the frequency distribution. I can't express enough how important being able to use frequency distributions to show how a variable is distributed in a population is to doing exploratory research. It is so critical. It tells you a lot about a lot of things, and whether it's turnover or it's comp or it's engagement scores or it's sales data or it's turnover data or it's promotion data, they can all be frequency distributed. And it's a really interesting way to explore your data. And now I've rambled us 5 minutes over time. Does anybody have any last questions before we call it a night?
Actually, for the week 4 vignette that we have to do, it says in there that there's 2 final scenarios, but I only see 1.
Yeah, that's just a misprint that Ben and I we're only giving you 1 this week because we're doing the descriptives this week. Next week you're going to do a similar exercise and it'll be for the inferentials, and then you will do the second half of vignette 4 in week 5, if that doesn't sound too confusing.
Okay.
So only 1 vignette this week, and then you'll have 1 vignette for next week, and the 2 of them combined will be your 70 points for the vignette 4.
Okay, thank you.
Cool. Anything else before we wrap up tonight?
All right.
I agree.
Thank you all for
All right, guys.
great week this week.
Have a
Meaty
great
content,
evening.
and you all doing great. This was good week. Good week.
Yeah. This is we're halfway through the hardest weeks.
I should have last night's class dropped into the Canvas tonight, and then I'll work on getting this one done first thing in the morning, guys.
Thank you.
You're
Thank
welcome.
you.
You guys are killing it. I'm so proud of you, just so you know.
Buenos
You're,
noches.
you're, you're doing great.
Buenas noches.
Thanks,